coherent optics.
Oh, thank you very much, Alan. Hello, as Alan already said, I'm Thomas.weible, co-founder and CTO at Flex Optics, specialized in optical transceivers. And today I have a topic with me about coherent pluggables or coherent optical transceivers. And in my personal point of view, it's going to be a game changer in optical transmission. And on this presentation, I will show why and how. And it's going to be split in two sections. So there's a little bit theory. There won't be an exam, no worries. At the end, and then there will be a practical, not an exam. So we did the exam actually together with the customer to implement it in a switch operating system and how we did the troubleshooting then. That's what I want to show then. So let's move on or start basically. So a little bit of history. DWDM or coherent technology was around or is around for quite a long time, a couple of decades. But so far it was only used on big transponder cards, which you might be familiar of your transport gear. And on that transponder card, to enable coherent technology, there is a DSP, a digital signal processor. In the past, they were big and huge because of manufacturing capabilities of how to produce a chip. And now we are able to really shrink it down to a really nice size to fit it on a QSF PDD form factor, which is pretty amazing actually. So yeah, the DSP is now built either in 7 or 5 nanometer technology, and it's really, really small. And that's mainly the thing I want to talk about today, this DSP. So, but where are we coming from? First of all, light has a couple of capabilities, and so far until, let's say, 40 gigabit, we only used one characteristic, the frequency. And on the top left corner, you see a typical rectangle shape of a diagram showing 2 states representing one symbol. So you have a state binary 1 and binary 0. I think this is straightforward. On the bottom one, that's how actually the receiver gets the signal. So it's more a sinus-shaped curve, and it's a little bit disturbed. So when we now increase the frequency, and you can imagine what happens, so it's getting more dense and dense, but the levels are also getting closer to each other. And that means for the receiver, it's getting way more harder to detect and differentiate between a 0 and a 1. And finally, the frequency is way too high. The receiver, it's just not detecting anything any longer. And that's a serious issue. So light has more properties. Beside the frequency, there is polarization, for example, and amplitude and phase. And polarization is straightforward. Quite a lot of people of you use it day by day when you look in your privacy screen on your laptop, that your coworker next to each of you can't look on your screen. That's actually polarization, what's happening there. So you can really form the light to a certain angle at the end of the day. For the coherent technology, we make use of 2 polarization angles or directions. And to give you a better view on it, we did a small simulation. So this here is a 16 QAM. To QAM I come later on. A signal on the Y plane. So it's one polarization direction like this. So we have Y plane and the X plane. And so when we run that simulation now and swap over to the X plane, that's the X plane now, also seeing our frequency diagram. And now when we combine both planes together, what's actually happening with a coherent transceiver, we get this nice and interesting, here we go, 3-dimensional form actually, and that's what hits the receiver, and he needs to detect this artificial art to be signals at the end of the day, 0s and 1s. So this was the first one about polarization. And as I already mentioned, we have this 16 QAM now. So what is this QAM? QAM is quadrature amplitude modulation, and with QAM also constellation diagrams were introduced. And this nice matrix, which you see now here, is a 4x4 matrix. And I'm going to explain it a little bit in detail. So it's a complex scheme, and within complex numbers at the end of the day in mathematics, we have a real and an imaginary part. The real part is in phase, and as a reference, I also pointed the dots or the squares in green, which is a PAM4 modulated signal. It's all in phase, so you have 4 states or 4 binary states representing 2 symbols. Or even the previous one mentioned at the beginning, it's an on-off keying, only 2 states with 1 symbol. These are the 2 stars. They are all in phase. Now in QAM, we have those 16 dots and representing 4 bits for a symbol. And that's how is it done? We shift the amplitude by 90 degrees. Or the phase, sorry. The phase is shifted by 90 degrees. And to give you a better understanding how this can be done, I took an example of the real world or the analog world. So that's an optical rotary encoder, typically used in servo motors to find the position. So how does it work? You spin the wheel and you see this. You can encode the zeros and ones with the cuts actually, the cuts in that wheel. And then you have 2 detectors. So the first one is the real part. You detect there's something, and then just physically moved a little bit later, there's the, I would call it now the imaginary part, a second detector. And we sample at the same rate, at the same time always that signal. And then you get something like a 90-degree phase shift. And the same happens in a coherent transceiver as well. We can do a phase shift. For sure, there is not a wheel inside. But this is more an analog example to understand the real and the imaginary part. Having said that, within coherent transceivers, another thing is very, very important now. It's the signal-to-noise ratio. So what is the signal-to-noise ratio? It is actually the ratio between your actual data and the noise which is on the line. Good comparison is like here in the audience now. You can hear me clearly and without any issues because you're very quiet. This is a good signal-to-noise ratio. And if I would do the same presentation in a football stadium where everyone is cheering, the SNR would be horrible bad. And it would be difficult to understand me. And now coming back again to the 16 QAM constellation diagram, and we look at the SNR now, you also see the difference there. So the SNR of 30 dB is a really clear shaped constellation diagram. The receiver can detect each 16 dots pretty easily and differentiate between them. If the SNR gets a little bit weaker, the dots are not real dots any longer. They are a little bit blurring. And now at SNR of 5 dB, it's just though you can't detect anything there. And yeah, that's important here to know. That's so far about the theory. So what did we do in practice? So we took a QSFP DD, plugged it in Nokia gear, which is operated by DKNOG in Germany, and we were looking at the implementation of on the SROS, how they use the coherent parameters, and I'm going to show them now. And we were just running one command. It's the show port command, nothing else. The first page, and there are 3 in total for the show port, is mainly the characteristics of the transceiver itself. It is a fully tunable DWDM coherent transceiver, and you see the min and max frequency. Here it's shown in megahertz. Typically we use terahertz, which makes the numbers a little bit smaller. So saying that these are 191.3 terahertz at the low end and up to a max frequency of 196.1 terahertz. Or in other words, channel 13 to channel 61. That's basically it. The transceiver is currently tuned to channel 23, and it is capable not only to support the well-known 100 gigahertz grid or 50 gigahertz, but also slices between like 75 or 25 gigahertz. So these are the capabilities of the transceiver. Then the next one, you should be familiar with that one so far. It's the diagnostic monitoring, and I hope everyone has implemented it in his NMS already. For sure, TX and RX levels are shown there, but I highlighted the temperature. And why do I highlight the temperature? The reason is just pure physics. So a transceiver is basically taking power and converts it to heat and a little bit a portion of light. And that's the ratio what we're seeing here. So when we feed in 17 watts, and that's the actually amount a coherent transceiver can draw out of your switch port, it's ending up of 16.999 watt of heat and only a little portion of light. So those 0.001 watts is 1 milliwatt, being 0 dBm, which is actually a high power level for light in a DWDM system. And it is important to mention the temperature because not every switch gear and router gear out there is supporting those 17 or even above watts on each single or dedicated QSFP-DD port. So you really need to go through the specs. If it's able, some vendors call it the high power mode, to provide that much power on a port, and sometimes they shut down every second port, for example, when you enable the high power mode, that you provide that power. So your 32 port switch is at the end of the day a 16 port switch. This can happen depending on the specs, how much power you can feed in, and way more critical, how much heat you can get out of that one U chassis, for example. And now, coming to the coherent parameters, this is like the juicy part. So I'm gonna go through them step by step now. The first one is the RX channel. This is new now. Previously, for tunable DWDM transceivers, like in 10 gig, you only did the tuning on the TX side. Now you have also locked the RX channel or the RX side to that channel as well, that the local oscillator inside of the transceiver is getting that frequency and knowing how to interpret the signal. There is no detection or sweeping, so we can't detect the channel. So you really need to lock the RX channel to the transmitting or matching to the transmitting channel from the counterpart interface. And the second one is dispersion. And we do have two types of dispersion. The first one is chromatic dispersion, typically in a range up to 2000 picoseconds. And the great thing about the coherent transceivers is they can compensate this dispersion. So there is no dedicated chromatic dispersion needed any longer. You can do it with the DSP to compensate that. And you see this on the lower part where we show the chromatic dispersion. That's the actually measurement. So we can even measure the dispersion on the line. And if you do the math and you know the characteristic of your fiber, so in this case we had 220 picoseconds per nanometer, and we had a G6.52D fiber, which has roughly 10 picoseconds per nanometer per kilometer. And if you do the math, you would end up at 22 kilometers, which is not true. The fiber actually was 15 kilometers in that scenario. And then we tried to figure out why. We couldn't figure it out because we should have seen there roughly 150 picoseconds per nanometer. So we did the counterpart test. We made a back-to-back link with just a jumper cable of 2 meters, and suddenly appears 80 picoseconds per nanometer there, and we have no clue where it's coming from. So there is somehow an offset, but at the moment we don't know where this offset is coming from. So this one was a 15 kilometer fiber. Beside the chromatic dispersion, as I mentioned at the beginning about polarization, it's not only the chromatic dispersion is basically the change of your signal while it's traversing on the fiber, the velocity, and now we can also have this with the two X and Y plane, with those two planes, that they change their speed levels while they are traversing on the fiber. And that's measured or shown as the different group delay. And here we have 2 picoseconds. And when you look in the specs, you can compensate up to 10 or 20 picoseconds of different group delay. Moving on, about OSNR, we also have now 2 levels of OSNR, not only one, so for each polarization plane. And this one was running at 34 dB, roughly a little bit more than 34 dB, which is very, very well, very good. We can go down to 24, 26, depending on the type of standard we are following. And after that, it's an issue for the receiver. An interesting part was the RxQ margin, and we figured out that Nokia development was quite creative there. Actually, we weren't able to map the Q margin to some what is in the telco or in the optical transmission world known value, and we identified the Q margin actually is the Q factor. So what is the Q factor? It is a measurement in a ratio again about the capabilities of the forward error correction, the FEC, until it's still capable to correct errors. So when this margin is eaten up, so when we are at 0 dB, the forward error correction is not able to correct any longer an error-free transmission on the post-FEC side. And here you see the pre-FEC errors as well. We don't see the post-FEC errors. And back-to-back link had roughly a margin of 4 dB, RxQ margin or Q factor. Okay, I'm gonna skip that. I want to point out to the differentiation now about the standards. There are two major standards defining now those coherent transceivers. The first one is the OIF 400ZR, and the other one is the OpenZR Plus. And until now, only TX and RX power were quite relevant when we designed an optical network. But now with the coherent one, you should also take in consideration about chromatic dispersion, the polarization mode dispersion, and the optical signal-to-noise ratio. And here you see the major difference between both standards. The OpenZR Plus is a little bit more, let's say, hardened. Especially, it's more tolerant for dispersion here. OpenZR Plus differentiate between low power and high power. This is the 60L for low power and A version A, and 60H for high power. I said at the beginning that the coherent technology with the DSP inside is somehow a game changer in optical transmission. And when we look at this screen now, it's actually just we can increase the bandwidth multiple times just with the fact that we use raw or pure compute power within a transceiver to increase our bandwidth. And this is an enabler also for upcoming technologies like 800 gig or 1.6 terabit or even beyond that. For sure, there are other mechanisms as well to do so. For example, increase the frequency again. So on the bottom line, on the x-axis, you see the frequency on the electrical side. And we are currently at 50 gigabaud running there already. So we could do 100 gigabaud as well, and that's also an intention. But just and this is quite difficult to implement as well. But with the compute power of the DSP, it seems to be way more easy to increase the overall bandwidth of a pluggable. This brings me almost to the end of the presentation. We did this test with Nokia gear, and we are more than happy to do it also with other vendors' equipment. If you have something, let us know, give us a ping, because it was a really nice workshop together. We learned on both sides, we learned quite a lot. When we did this with DKNOG. Thank you very much.
Are there any questions?
Thank you.
No? No questions?
All right. Thank you.
Then I would just say thank you very much, and here's
perfect
for you.
Thank you very much, Alan.